Now let us talk about the Laplace transform of elementary functions. Before that, once again, I want to write the original definition of Laplace transform. Laplace of f of t, you can write like f of s also, and the formula is integration 0 to infinity e raised to minus st f of t dt. This is the standard formula where t greater than or equal to 0. Now, one by one, we are going to prove the formulas of Laplace transform of elementary function. Now, before going for the next step, I want to give the formula of hyperbolic function because many of you don't know what is the logic of hyperbolic function. Okay, so hyperbolic function means whenever you are writing cos hyperbolic at, it means e raised to at plus e raised to minus at divided by 2, and sin hyperbolic at, that means e raised to at minus e raised to minus at by 2. Okay, so this is the original formula of hyperbolic function, cos hyperbolic and sin hyperbolic. I am going to use these two formulas in this proof. First of all, cos hyperbolic. So let us implement this one. So Laplace of cos hyperbolic at can be written as integration 0 to infinity e raised to minus st cos hyperbolic at dt. Instead of this hyperbolic function, I am substituting this form. So integration 0 to infinity e raised to minus st e raised to at plus e raised to minus at divided by 2 dt. We know we can apply the integration separately in this form, like linearity property of integration. Okay, so we will do it. I'm just removing this form. So first of all, note down this one. Okay, fine. So write down separately. So you can write 1 by 2 integration 0 to infinity e raised to minus st e raised to at dt plus integration 0 to infinity e raised to minus st e raised to minus at. Now you can do separate integration and you will get the answer. This is nothing like the second form Laplace of e raised to at, and third form which I will give you as a homework, e raised to minus at. So you can do the integration. It is not difficult. Okay, and if I don't want to take the integration, then I can use the ready-made formula of Laplace of e raised to at and e raised to minus at also. So here I can write 1 by 2 Laplace of e raised to at plus Laplace of e raised to minus at, because this is the formula of Laplace of e raised to at and this is the formula of Laplace of e raised to minus at. We know the formulas of Laplace of e raised to at and e raised to minus at. Apply it. So what we can write? We can write 1 by 2 into the bracket 1 upon s minus a 1 upon s plus a. Take LCM. So 1 upon 2 s plus a plus s minus a upon s square minus a square. Simplified, a will cancel. In numerator 2s, 2 will cancel. Final answer is s upon s square minus a square. Now what is the difference between the answer of cos hyperbolic at and cos at? The Laplace transform of cos at is s upon s square plus a square. And for the hyperbolic function, Laplace transform of cos hyperbolic at is s upon s square minus a square. So the difference is just for sign. Okay, both the formulas are same, but in that form, in denominator it is positive sign and this is negative sign. Okay, the procedure for sine hyperbolic it is quite simple. Just you have to implement the different formula of that sine hyperbolic function which I have given you. Okay, so I am not giving the proof of that form. I am giving directly the answer, that is if f of t is equal to sine hyperbolic at, then Laplace of sine hyperbolic at is a upon, can you predict the answer? What is the answer of Laplace of sine at? It is a upon s square plus a square. This is hyperbolic function. A upon s square minus a square. Is it okay? And I've given this as a homework. Do yourself. Tell me the difficulty. Okay. For the now we have only one function remaining, that is t raised to n, and that is very important, t raised to n. Formula number 8, f of t is equal to t raised to n. Okay, so Laplace of t raised to n is integration 0 to infinity e raised to minus st into t raised to n. How to take the integration of this form? For that, you have to assume something. What is the assumption? Take this power as the assumption. Take st is equal to u. Take the assumption. I need dt also, and I have to change the limit also. Let us first of all think about the limit. If t is equal to 0, put it here, so u is also 0. And if t tends to infinity, u tends to infinity also. So there is no change in limit, you can observe. If I am taking the derivative of this form, so s remains as it is, and derivative of t is dt, right hand side is du. Okay, substitute all this information in this form, so what you will get? You will get the limit remains same, e raised to minus st, that means e raised to minus u, and t raised to n, that means instead of t, from here, instead of t, what you can write? From here you can write t is equal to u by s. So right now that is u by s raised to n, and instead of dt you can write from here, instead of dt what you can write? Dt is equal to du by s. So here we can write du by s. Now s is constant, so you can take it outside. So I can write like 1 upon s raised to n plus 1. Why it is s raised to n plus 1? S raised to n from here and 1s from here. So s raised to n plus 1, integration 0 to infinity, e raised to minus u, u raised to n du. Now have you seen this formula before this concept? So the answer is yes, this is gamma function. Okay, what is the formula of gamma function? I will tell you. What is the logic of gamma function? Gamma function says that gamma of n plus 1 can be written as integration 0 to infinity e raised to minus x, x raised to n dx. If you have this type of improper integration, so you can write the answer as a gamma n plus 1. So just look at both the integration. Instead of x, here u is given, that's it. Right, so this is what? This is nothing but gamma n plus 1. So the final answer can be written as gamma, here I'm writing here separately, Laplace of t raised to n is equal to gamma n plus 1 upon s raised to n plus 1. Laplace of t raised to n can be written as gamma n plus 1 upon s raised to n plus 1, because this is gamma function. Okay. Now we have little bit knowledge about gamma function. So let us apply that knowledge. What is gamma function's logic? If you have this gamma n plus 1 is equal to integration 0 to infinity v raised to minus x, x raised to n dx, then what you can write? You can write gamma n plus 1 as a two different situations. You can write like n factorial, and sometimes you can write n gamma n also. When n factorial comes, if n is positive integer, and this is for fraction parts, or you can say if it is not positive integer. So here I am writing otherwise. Otherwise that means if first is not there, you have to apply second. Okay, right? So now I'm giving you two examples of this gamma function. Suppose I want to find the gamma of 5. So what is the answer? Which formula is applicable? First one or second one? First one. Why? Because here 5 is integer. So what is the answer? Answer is 4 factorial. Why I am writing 4 factorial? This 5 is n plus 1. So what is n? N is 4. So 4 factorial. You can evaluate the value of 4 factorial. You know what is factorial notation, right? And suppose I want to find the answer of gamma 3 by 2. So this is what? This is n plus 1. If n plus 1 is equal to 3 by 2, what is n? n is 1 by 2. So gamma 3 by 2 can be written as 1 by 2 gamma 1 by 2. Now in mathematics, we have the value of gamma 1 by 2. Okay, note down if you don't know that. Gamma 1 by 2 can be written as under root pi. So we can simplify this as gamma 3 by 2 is equal to 1 by 2 under root pi. Okay, right? So here I have given you the basic information of gamma function which we need in the Laplace transform. Okay, so just note down this concept and then we will go back to the concept of Laplace transform. Okay, so what is the formula of Laplace of t raised to n? Once again I am asking you, what is the formula? So gamma of Laplace of t raised to n is what? Gamma n plus 1 upon s raised to n plus 1. Okay, and this means you have two answers, n factorial upon s raised to n plus 1 or n gamma n upon s raised to n plus 1. When this formula is applicable, if n is positive integer and this is otherwise that means if first one is not possible, you have to apply this one. Okay, so many students are making mistakes in this result, so just be careful in this result. Okay, so here the Laplace transform of 8 standard elementary functions we discussed. Now let us list out once again the formulas. So it is just one type of revision. Here I am writing two columns. Left hand side is f of t and right hand side is f of s. Two columns. So f of t, f of s. What is f of s? F of s means Laplace of f of t. Same way, f of t, f of s, that means Laplace of t. Because the space is not enough, that's why I have to take two parts. So let us start with a. Laplace of a by s. E raised to at, 1 upon s minus a. E raised to minus at, 1 upon s plus a. Cos at, s upon s square plus a square. Cos hyperbolic at, same, but the sign is different in denominator, s square minus a square. Sin at, a upon s square plus a square. Sin hyperbolic at, a upon s square minus a square. And now the important formula comes once again. T raised to n gamma n plus 1 upon s raised to n plus 1. You can write like n factorial upon s raised to n plus 1 or n gamma n upon s raised to n plus 1. This is for what? If n is positive integer. Okay, and this is otherwise. So I hope friends the concept of how to evaluate the Laplace transform of elementary functions are clear. Okay, in next lecture we will discuss linearity property and then the Laplace transform of piecewise continuous function and the next topics. Thank you very much.